Each spot that you see here represents an individual galaxy. Filamentary structures are assigned distinct colors to help you distinguish different components. The major clusters are colored red. Now all the galaxies are assigned the same neutral color. Our Milky Way galaxy is at the center of the cube. The display is in supergalactic coordinates. The SGX, SGY, and SGZ axes are colored red, green, and blue respectively. The distance from our galaxy at the center to a wall is 3,500 kilometers per second, or roughly 45 megaparsec. There are 7,000 known galaxies in this volume. Eighteen hundred of these galaxies have accurately measured distances. These galaxies are given colors here that indicate the deviation of their velocities from the cosmic expansion. Galaxies that are deviant in the sense that they have motions toward us are colored blue. Galaxies that are moving away from us relative to the cosmic expansion are colored red. In these scenes, the cosmic expansion is characterized by a Hubble constant of 70 kilometers per second per megaparsec. Note the preponderance of red in the upper half of the scene, indicating a general expansion away from us in that sector. By contrast, there is a preponderance of blue in the lower half of the scene, indicating a flow toward us in that sector. The cosmic expansion is now characterized by a Hubble constant of 80 kilometers per second per megaparsec. Note the much greater preponderance of blue, indicating motion toward us. Even so, there is a sector of the cube that is still dominated by the red of motion away from us. Roughly 600 of the galaxies with distance measures are given big symbols. In these cases, distances are from the Cepheid period luminosity relation, or the tip of the red giant branch or surface brightness fluctuation methods. These distances have accuracies of 5 to 10%. The small symbols represent the 1,250 cases with luminosity line width distances. The accuracies for these are 15 to 20% each. Now, the cosmic expansion is characterized by the intermediate value of the Hubble constant of 74 kilometers per second per megaparsec, the value that gives the best fit to the available data. This value of the Hubble constant will be assumed for the rest of this presentation. The color coding for peculiar velocities is now more elaborate. Progressively large negative velocities are light and dark green, then light and dark blue, while progressively large positive velocities are yellow, orange, red, and brown. There is a preponderance of blue in the bottom of the volume and in the most populated sector of the upper part. The less dense sectors of the upper volume tend to be reds and browns. Vectors emanating from the positions of the galaxies with measured distances provide an alternative display of peculiar velocities. Negative velocities are indicated by blue vectors pointing toward our position at the center. Positive velocities are indicated by red vectors pointing away. The very nearby galaxies in the equatorial plane of this display are mostly yellow and light green. These galaxies show only small deviations relative to an expansion law. Below the equatorial plane, the pattern of blue indicates approach. We move to a band that isolates the main part of the local supercluster with the Virgo cluster at the densest location. Here we are looking north of the plane of the Milky Way toward positive SGY in supergalactic coordinates. Notice the overwhelming preponderance of blue in the vicinity of the Virgo cluster near the center and everywhere in the lower quadrant. There is a fair representation of red-brown on the midplane at SGX strongly negative in the proximity of the Centaurus cluster. Consider now the structure lying to the south of our galaxy. The concentration of blue objects at negative SGZ are in and around the Fornax cluster. In the extended region higher SGZ, the galaxies are largely colored shades of yellow, red, brown, indicating motions away from us. The orange vector emanating from our position at the center of the box shows our motion with respect to the ensemble of galaxies within 3,000 kilometers per second with measured distances. We now isolate a region immediately around our galaxy. Let us give it a closer look. The dense blob of blue near the right boundary is the Virgo cluster. Appreciate that for the most part it is not that the Virgo cluster is moving toward us, but rather that we are moving toward the Virgo cluster. Surrounding us, most galaxies are colored yellow and light green, indicating only small relative motions. If our galaxy has a peculiar motion, it is shared by all our nearest neighbors. We are all moving together. The other obvious feature of this region is the predominance of blue associated with galaxies below the equatorial plane in what I have called the Leo spur. Is the Leo spur falling toward our cloud? The orange vector representing our motion with respect to galaxies within 3,000 kilometers per second can be partitioned into two components. The blue vector points toward the Virgo cluster, a known source of attraction. The red vector is the residual. It points away from the local void. Note the lonely blue galaxy above the supergalactic plane in the opposite sector from Virgo. This galaxy lies within the local void and has a large velocity toward us. Let's recall the overall distribution of galaxies in the local supercluster. Note the lack of galaxies in a large volume above our local filament. The extensive pattern of blue around Virgo can be attributed to a collapse toward the Virgo cluster that we participate in. We see that the pattern of blue at negative SGZ is more extensive than just the region of the Leo spur. There is a bipolar symmetry between this blue pattern at negative SGZ and a red pattern at positive SGZ. The strong inference is that we, along with our neighbors, have a pronounced peculiar velocity toward negative SGZ as well as toward positive SGY. The positive SGY motion can be ascribed to the pull of the Virgo cluster. The negative SGZ motion is suspected to be due to the push of the local void. We attempt to represent the region of the local void with three ellipses. The region of low density at plus SGZ is extensive, but in detail there are wispy filaments that cause us to separate the volume into three separate void regions. We will call the nearest empty region the inner local void and the more distant regions the local void, north and south. As before, The orange vector represents our motion with respect to galaxies within 3,000 kilometers per second, and the blue and red vectors are the decomposition of the orange vector into components toward the Virgo cluster and away from the local void. Now we add the cyan vector, which indicates our motion with respect to the cosmic microwave background. And we add the brown vector, which is the residual of the subtraction of the orange vector from the cyan vector. Hence, the brown vector is the component of our motion with respect to the cosmic microwave background that is caused by structures on scales greater than 3,000 kilometers per second. We have just added the distribution of Abell clusters of galaxies in a box bounded at 20,000 kilometers per second on the cardinal axes. The distinct colors identify groupings of at least 8 Abell clusters with friends of friends pairwise separations less than 3,000 kilometers per second. Near the center of the volume, mostly within the inner box, there are 8 clusters colored cyan. These rich clusters include Centaurus, Hydra, Norma, and Virgo, and constitute what came to be called the Great Attractor region. The brown vector, which identifies our motion caused by large-scale influences, is pointed almost at the Centaurus cluster. Take notice of the large number of symbols colored red just behind these central cyan objects. This is the Shapley concentration of galaxies. It remains to be resolved how much of our motion induced on large scales is due to the supercluster including Norma, Hydra, and Centaurus at 3,000 to 5,000 kilometers per second, and how much is caused by the Shapley concentration at 15,000 kilometers per second.